What are the types of chemical reactions? Lots of chemical reactions have very clear signs that they've taken place, as we've already discussed. In the picture, we can see several very interesting looking chemicals. What happened if we mix them together? And how do we know? In this lesson, we're going to learn about the different types of chemical reactions. Let's talk about types of chemical reactions. There are lots of different types, but we're going to focus on the 5 main types of chemical reactions. The first of these is synthesis. Synthesis is a reaction in which we have 2 reactants coming together to form a new product. So it might look like this. We might say A plus B forms AB. Okay, so far so good. The next one is decomposition, and it's the direct opposite of synthesis. It's where things come apart. We've heard that word decompose before. So this is a reaction where we have a single compound breaking into multiple products, or its component pieces. It might look like this. AB forming A plus B. Okay? The next one is combustion. And this is basically a reaction of any substance with oxygen. It is that simple. So we look at our substance, and we have oxygen, and we will have a product that includes an oxide of our substance. Okay? The last 2 are great because their names help us to remember exactly what's going on here. Single replacement. This is a reaction where one ion displaces another to form a new compound. It also replaces. These are the same words, displace, replace. We can use these 2 words interchangeably in this instance. So let's look at it. It might look like this. We have A plus BC, and once they've formed, they create a new compound of AC and a new element, looking very different from the original reactants. The next one, again, that great name helper, double replacement. This is a reaction where we have 2 ionic compounds exchanging or swapping over ions to form completely new products. So that might look like this. AB plus CD forming 2 new compounds, 2 products. There we are. So let's look at some examples of these. Let's start with the first 3, specifically synthesis. Here we have the reaction. We have our sodium, our chlorine, and what they make. Here we have A plus B forming AB. Okay, sodium and chlorine forming sodium chloride. Next, decomposition. Remember we said that this was the opposite of synthesis, coming apart. So we have our water molecules. We have that compound, that AB. And after the reaction of decomposition, we have our water, our hydrogen, and oxygen. Those component parts, now gases. And then we have the combustion. Remember we said that it's any reaction that involves oxygen as a reactant. Here we have propane and our oxygen. And after our reaction, we have, remember we said we were going to have an oxide, here it is, carbon dioxide. Oh, can I get that in there? I can. And water. Let's look at that again. Let's look at combustion again in a slightly more simple way. We'll look at this. If I have the magnesium and the oxygen, we know that magnesium, if it's interacting with oxygen, must be a combustion reaction. And indeed, when we finish, we see that when it's finished, we have magnesium oxide. That's not all that's going on. Did you see it? I also have this. I have that single reactant and another reactant forming a product. It's also a synthesis reaction. Okay, so one of the ways we might look at that is if any of the reactants in a synthesis is oxygen gas, in a synthesis reaction is oxygen gas, it's also a combustion reaction. Let's recap. Very simple, in a nutshell, synthesis. Multiple reactants forming one product. Decomposition. One compound, one reactant forming multiple products. And combustion. Oxygen always involved as a reactant and a product always including an oxide of that reactant. Let's come back to those last two of the 5 main types of chemical reactions. Those are the single and double replacement. And remember I said that these two actually, their names help us to remember what's actually taking place in these reactions. Let's start with an example of single replacement. Here we have an iron oxide. We have an AB. And we have aluminium. Sorry, you say aluminum. There we go. There's our element. Remember we said that the element in the reactant was now going to be in our compound, in our product compound. Here we see it. We've got aluminium oxide and iron, a new element. Okay, let's look at another example of single replacement. I have magnesium, A, and I have water, BC. When that single replacement reaction is complete, I'm going to have magnesium oxide, an AC, and I'm going to have some hydrogen gas, our new element. Did you also notice that with the oxygen in both of those examples, that makes it a combustion reaction as well? I'm sure you did. Let's look at double replacement. Remember we said that that's where the ions switch over. Let's see how that works. Here I have a lead nitrate. So I have an A, B, and a potassium iodide, C, D. When that double replacement reaction is complete, I'm going to have a lead iodide, as is beautifully depicted in our photo here by the green precipitate, and I'm going to have a solution that has potassium nitrate. So I have C, B. Now, let's recap. In a single replacement reaction, I have one reactant as an element, one reactant as a compound. In a single replacement, I have one product as an element and one product as a compound. And remember I said that the reactant element is now going to be part of the compound product. In a double replacement reaction, both the reactants and the products are ionic compounds. And the same ions are going to be present in both the reactants and the products. Okay, and that's particularly important when we start looking at polyatomic compounds. If the ions haven't changed their form, if they're still the same in the reactant and the product, it's a pretty good bet that there is a double replacement reaction taking place. However, if, for instance, that one of those ions has changed form, so perhaps from a sulfate to sulfur dioxide, then you're probably not looking at a double replacement. Now you know that an element can replace an ion in a single replacement reaction. How do we know whether two substances are going to react? I call these the what-if equations. What if I took some silver and put it in a copper nitrate? What if I had a copper wire and put it in some silver nitrate? What would happen? Only one of these equations can proceed spontaneously. That is, without outside energy. But which one? Well, now you'll learn about a concept that chemists use to predict relative reactivity. So predicting outcomes of a reaction. Remember I said that chemists use the activity series. Here it is. What it does is it's a description of the relative reactivity of the elements. And here what we have, we start at one end, and at the left it's much more reactive. And at the right it's less reactive. And there's a series of metals. So we start at the very reactive lithium and move along to the much less reactive gold. And if we think about it, maybe in terms of reading, if you started out reading a passage at one end, by the time you were finished, you might have run out of a little bit of steam. So in this example of the activity series, we can see that the lithium is at one end, gold is at the other. It might look like cadmium is a lot less reactive because it's on the right-hand side than, say, cobalt. But that's just because of the space on your slide. We just didn't have the ability to put it all in one very long line. But that's how it should be, in one very long line. So what we can see is that potassium is much more reactive than magnesium. Okay, we can see that nickel is much more reactive than bismuth. What we can also see is that zinc is much more reactive than hydrogen. Does that make it clearer? I hope so. We can also do this with the halogens. The activity series shows us that the much more reactive fluorine is to the left of the much less reactive iodine. So let's use that activity series to make those predictions. Let's go back to those what-if equations we had. Which of the following reactions will take place? Will it be the silver nitrate and the copper coil, or will it be the copper nitrate and the silver coil? Here's our metals activity series. Okay, so first what we need to do is find our elements on them. And here we have the copper and the less reactive silver. So we see that copper is more reactive than silver. Now, when an element is in its pure state, what happens is the more reactive it is, the less stable it is. Or if you like, an element in a compound is offered stability by that compound. So, again, as a pure element, the more reactive it is, the less stable. So that's where the reaction will occur. What we see in our example is that the copper is in its pure form. And we know that according to the activity series, it's the more reactive. So I predict that's the equation that's going to proceed. Let's look at how that equation will look. And we'll do it this way. So I've got the silver nitrate and the copper coil. And after my reaction, I'm going to have that new element of silver. There we are.